Hello and welcome to another video. This one has been long awaited by some of you. Today I'm going to give you an introduction to what Docker is and hopefully explain some of the basic concepts behind it, but I'm going to try and avoid going into too much detail. And I guess more generically I'm going to talk about containers as well. Docker is just a particularly popular implementation of containers. Containers themselves aren't really a new concept. They've been around for I don't know, tens of years, like in the forms of like ch roots or jails or other sorts of things like that. But we're going to specifically talk about the type of containers that were popularized by Docker in the last 5 to 10 years. And I guess before we talk about containers themselves, it's useful to talk about what a Linux system is. And I have a little MS Paint drawing ready for that to kind of talk about what Linux is. And when people refer to Linux as kind of the group of operating systems, what they're really referring to is the Linux kernel and then some user space on top of that. And so this user space is usually what you might refer to as your Linux distributions. This might be like Ubuntu or Fedora or CentOS or some other user space collection of software. And this is a collection of software that's built against some specific kernel, and the kernel the kernel implements all of the like process scheduling, memory management, system calls, and all that other stuff. And that's what's referred to as the kernel. So I use Ubuntu 2004. That is a collection of software built on top of a particular kernel. And if we find, yeah, I am currently using, it looks like, oh, those are purged. Where's the current version? I'm currently using the kernel 5.4.0-53. And this is a particular build of a particular version of the Linux kernel. And then all the rest of the software on my machine is built on top of that. And that's in the user space. Now the user space actually kind of has two sort of segments to it. We won't go into too much detail there, but there's like the system user space and then the user space where you don't need privileged things to operate with files and stuff. But it's all separate from the kernel, and the kernel is like the very, very privileged space. And the cool thing about containers, the way that they're actually enabled, is they share the kernel with their host operating system, and they swap out whatever this user space is. So if I wanted to start a Ubuntu container here, so let's say this is starting the Ubuntu, I don't know, Ubuntu Focal container. And we'll go over more details about images and containers in a bit, but what the operating system does kind of at the low level is it maps this kernel into this container. You can think of it this way. It's not actually how it works. It actually works with some special, kernelized things. But you can imagine that it pulls in the kernel here, and so we get this same, kernel space here. But then we might have some other implementation of this user space here. So let's say, our host machine is maybe Fedora, and so this is a different user space over here. Let's pick a color that's kind of render fine. So this is, a different container. It shares the same kernel, so all of the same system calls happen, but the operating system sitting on top of the kernel will operate in a different way. And you might imagine, if you could run any operating system in this, or any Linux-based operating system in the same way, because it's just going to rely on the kernel being there. Now, what makes this different from virtualization or virtual machines, which is one way that people often talk about containers, because they're very similar ideas. Like you take an operating system that's different than yours, and you run it on top of it. The thing with containers, though, is they're sharing the kernel. A virtual machine is actually going to give you an entirely separate kernel and potentially a separate even operating system. So you can imagine like this is a container here, but if we were to look at like some, oops, that's the wrong color. Let's make this black. If we were gonna maybe run, I don't know, a different virtual machine here. So let's say this is a VM. You would have an entirely separate, where's the square drawing box? There we go. You would have an entirely separate kernel here that might be, I don't know, it might even be a different operating system. Like this might even be like the NT kernel. Oh, that's not readable because it is the wrong color. So this might be, I don't know, a Windows user space here, for instance. But yeah, a virtual machine is not going to reuse the same kernel, and this is part of the reason that containers are really fast to start up, because they don't really have to start anything. The kernel is already there. They're really just running normal Linux processes on top of it. Okay, but anyway, that's kind of the low-level Linux parts of this. Let's talk about what makes Docker tick and why it is so much more popular than containerized solutions that happened before. And most of what makes those super popular, and I'm actually gonna, I'll probably make another drawing for this. Most of what makes them super popular is the startup time of them, and the ease of use of downloading particular images and running them quickly. So I'm gonna run, in this case, Ubuntu Xenial, which is an older version of Ubuntu. And you'll notice that it starts pretty quickly. I didn't have to like wait for a virtual machine to boot completely. I didn't have to wait for a huge file download. Actually, I think I already had that one downloaded. Ubuntu Xenial. This command's taking a while. That's weird. Wait. Oh, I just have to grab Xenial, that's why. This image should be, yeah, it's about 100 megabytes, so it's not a huge download, and it's, you know, relatively easy to start and stop. So, you know, some other previous alternatives would require you to do a complicated build process in order to build a CH root that had particular files in particular places, and like it was still possible to containerize, but there wasn't a popular, you know, image format to, you know, download and start running. And the way Docker does this, or at least the way the container, the OCI spec, Open Container Initiative, something like that, dictates the containers, is they are a specialized layer file system, and this is what allows containers to go really quickly, or start really quickly. And I guess before we talk about, you know, containers and images and what's different there, the image is the like bytes that represent the user space of your container, and the container is the running version of that. If you were thinking about like executables on a Linux machine, the file on disk is like the image, and a program running that executable is like the container. But the way that it works is they are a specialized file system which is composed of layers. Let's imagine that the layers go from the bottom up here. So this is like the very most, you know, basic layer here. This is a similar drawing to what I did before, but this is a particular image. So let's say this is, I don't know, my image. And maybe these bottom layers here come from whatever my base image is. Let's say that these all come from my base image, which might be like Ubuntu Focal. And usually this will be a series of instructions that were run in the builder. Maybe it's a series of copies or runs or whatever. This is another copy. You can actually look at the implementation of this by either looking at a Docker file or looking at Docker history to figure that out. And maybe this is my own set of runs. Maybe this was run apt-get install foo. This is obviously not what I would actually write in my Docker image. I'll probably do another video on that at some point. Maybe this is copy dot or something. Maybe to copy files into my image. But the neat way that this works is all images that are based on a particular base image will share the file system of the lower layers. So this means that you don't need to do a big copy when you're starting a container. You just, you know, sort of have a pointer reference it to these, and these are immutable, meaning they can't be modified. When you start a container, so let's say we started my image, we can make another box here. This will be our container of my image. It again will do sort of a pointery thing here where it maps this container image into here. So we have like a mapped file system here, and it builds another separate layer on top, and this is where writes will happen. So this is the, you know, temporary write layer. And so all you really need to do to start a container, well, there's a whole bunch of kernel magic-y stuff, is you have to allocate sort of a temporary layer and then point the rest of the file system at this layered file system. Now, layered file systems are pretty complicated, so I won't go into a lot of details here, but this is how you can kind of think of them. If you were to do a write, such as like a delete or changing the contents of a file, it's going to only write to this container here. But if you did a read, it's going to have to check each of the various layers. So let's say we were, catting / foo. So we're looking for, read / foo in some way or another. And the way the file system implementation works is it's going to try each layer in order. So it's going to say, is it in this layer? Nope. Okay, we'll try the next layer. Is it in this layer? Nope. We'll try the next layer. And maybe this is the layer where it's defined, so it might have found that file here, and then it would continue with its file system as it goes. So you can kind of think of the image format for Docker as like a linked list of file bundles. And that's what enables it to go super quickly. And the nice thing about speccing out a particular file system format is anyone can create these images and share them. And that's usually done through a Docker registry. So you can download a particular image, you can build new images, etc., etc. But yeah, that's kind of the low-level things and how it works. And now let me show you some of the magic of Docker. So the cool thing that I use Docker a lot for is to build software where I would need root, or I would need other operating systems, or I would need particular sets of software installed. And I can just download a pre-built image without modifying my own operating system, because I don't necessarily want to install a bunch of software globally on my machine. I'd rather put it in a container and deal with it in that way. So let's look at some of the containers that I have. Docker images is a way you list your images that are installed. Sorry, I said let me list the containers. I meant to say let me list images. It's really easy to mix up the word image and container. In fact, a lot of popular cloud providers actually make this exact same mistake. So if we look at like Amazon ECR, this is the Amazon Elastic Container Registry. However, it doesn't store containers, it stores images, which is, yeah, easily store, manage, and deploy container images. Images, not containers, images. Anyway, everyone makes this mistake, and it's really easy to slip up the two words there. So I like to try and be pretty careful, but you can see even I make the same mistake here. But yeah, let me show you like an example of where I use Docker to do development for Precommit. Precommit is the GitHooks and linter framework that I created. But I have a very specific Docker file in here. This is what a Docker file kind of looks like. It's a series of instructions. A from says where you're going to get your base image from. A run will run particular commands. Env allows you to set environment variables. There's a whole bunch of other commands. I'm not going to go into them in this video. But in this particular case, I wanted a isolated image on a particular operating system that didn't have binary installations of a particular library. So Precommit depends on YAML, and YAML can either be pure Python or it can have a binary dependency. And so I wanted a way to make a Precommit distribution where I don't have the binary dependency. However, on my machine, I have libyaml dev. I have this installed, and I didn't want to have to uninstall this every time I wanted to try and make one of these distributions. So what I did is I used an older version of Ubuntu, and I made sure to intentionally not install this dev library so that I don't end up with a C extension, and then I can build this as a separate image. Let's actually delete this image. Docker RMI this. You'll also notice this output is slightly different if you're using Docker at home, and this is because I'm not actually using Docker. I'm using Podman. Type Docker. Link which Docker. Yeah, so I'm actually using Podman, which is a different container implementation, but it tries to be very compatible with Docker. I'll actually probably do another separate video about Podman in general. But if we take this image, cd workspace precommit testing zip app Docker file, we don't cd to the Docker file, right? Docker build -t test dot. This will create an image called test using the workspace at dot. And you'll see that it's going to run these particular commands in a special container and build me a new image. This is going to take a while because it has to install a bunch of software. But this allows me to build, an operating system where I don't have LibYAML installed, which is pretty cool. But yeah, anyway, this is kind of a broad but also deep introduction to Docker. Hopefully this is somewhat useful. I'm gonna make a bunch of other videos about Docker as well, so this is not the last you'll hear of this. But anyway, if you have additional things you want me to explain, leave a comment below or reach out to me on the various platforms. But thank you all for watching, and I will see you in the next one.